Hi folks, this is Şefik. Today we are going to give a kindly proof of Fermat's little theorem by induction. This is one of the most important theorem in applied cryptography because RSA encryption algorithm is mainly based on Euler's generalization of Fermat's little theorem, and we are actively using RSA algorithm in encryption, key exchange, and digital signatures. We recently proven the Euler's generalization of Fermat's little theorem with number theory in this channel, and also we proven the Fermat's little theorem with netlist method. Today we are going to give an induction proof of Fermat's little theorem. But before we begin, please like the video, do not forget to subscribe to the channel and click the bell icon to stay up to date with the latest videos. Thank you for your all support in advance. Let's remember both Fermat's little theorem and Euler's generalization. Fermat's little theorem states that a to the power of p minus a is identical to 0 in mod p. Here p must be a prime number, whereas a and p must co-primes. On the other hand, Euler's generalization depends on a tangent function of n. It counts the positive integer numbers that co-prime to n. Therefore, a to the power of tangent function of n minus a is identical to 0 in mod n. Here, n doesn't have to be a prime number in contrast to Fermat's little theorem. We already know that this statement is true if we replace the a value to 0. 0 to the power of p minus 0 is identical to 0 mod p. Any power of 0 is going to be 0, and 0 minus 0 is going to be 0. So this statement is true. Similarly, we already know that this statement is also true for a is equal to 1, because 1 to the power of p minus 1 is equal to 0 mod p. Any power of 1 is going to be 1, and 1 minus 1 is going to be 0. Remember that p must be a prime number, that's why power of p must be a number greater than 1. That's why this statement is always true. Once we know these statements are true while a is equal to 0 and 1, then we are going to skip the a value to n. Currently, we don't know that statement is true, but we are going to suppose that this statement is true, and n to the power of p minus n is identical to 0 for mod p. Thereafter, we are going to try to prove the Fermat's little theorem while a is equal to n plus 1. If we can prove this statement is true, n plus 1 to the power of p minus n plus 1, if this is identical to 0 for mod p, based on the assumption n to the power of p minus n is identical to 0 in mod p, thereafter we can prove Fermat's little theorem by induction. To sum up, all we have is this assumption while a is equal to n to prove the Fermat's little theorem while a is equal to n plus 1. Here, to find the value of n plus 1 to the power of p, we can use the binomial theorem. It states that x plus y to the power of n is equal to n choose 0 times x to the power of n times y to the power of 0 plus n becomes stable, whereas the second value is increasing. Thereafter, n choose 1 times x to the power of n minus 1 times y to the power of 1. As you can see, power of y is increasing, whereas power of x is decreasing. Similarly, the third term is going to be n choose 2, and again the power of x is going to decrease, x to the power of n minus 2 times y to the power of 2, and finally n choose n times x to the power of 0 times y to the power of n. As you can see, it's going to be n plus 1 terms in the expansion of x plus y to the power of n. If we replace the x value to n and y value to 1 and finally n value to p, we are going to have the expansion of n plus 1 to the power of p. Here we know that n power of 1 is going to be 1 again, and if this is a multiplier, we can simplify these terms with removing 1 multipliers in those n plus 1 expressions. Then it's going to be more simplified. So we found the simplified version of n plus 1 to the power of p. Let's put those expansion into the main term in the Fermat's little theorem, and that's why I'm going to add minus n plus 1 on the right hand side. In this expression, we know that both p choose 0 and p choose p, they are both equal to 1. So we can simplify this expression as shown here. Thereafter, we can simplify plus 1 and minus 1 terms. And in this final statement, we can move minus n to next to the n to the power of p, because thereafter this term is going to be similar to the assumption we are currently applying. Here we suppose that the term on the left side is divisible by p, and if we can prove the following term is divisible by p, then we prove the Fermat's little theorem. That's why let's focus on the term except the assumption. So we are going to focus on this expression can be divisible by p, and we know that if each combination multiplier is divisible by p, then this term is going to be divisible by p. Here let's remember the binomial expansion and Pascal's triangle. We can find out the coefficients in a binomial expansion with this Pascal's triangle, and for example, if p is equal to 5, thereafter these lines values are going to be the coefficients for the combination terms here. P must be a prime number in Fermat's little theorem, and that's why we can discard the lines row values for non-prime numbers. Here all lines are beginning and ending with value 1, and please remember that we simplified the p choose 0 and p choose p coefficients in the previous page. That's why all these combination coefficients are going to be highlighted with yellow boxes. Please notice that if p is equal to 7, then yellow boxes are numbers that divisible by 7. Similarly, if p is equal to 5, thereafter yellow boxes can be divisible by 5. If p is equal to 3, yellow boxes can be divisible by 3. So all these combination coefficients should be divisible by p according to the Pascal's triangle. But could it be a line not satisfying this pattern? Because this is not a proof. We can prove that all these combination coefficients can be divisible by p with necklace method. For this task, let's suppose that p is equal to 7 and we have an alphabet consisting of 7 numbers, and I'm going to produce strings length of 4. In other words, I'm going to produce this number of strings 7 choose 4. Please remember that order is not important in combination. What does it mean? If I have a string 4 7 choose 4 1 3 5 7, the second expression is going to be the same string because it consists of same letters, just order is changed. It's same in the third and fourth expressions. I just have one string in this line. So how can I produce a new string from a given string? The answer is increasing all items one by one for mod 7. Similarly, for the string, if I'm going to increase the all items 1, thereafter I'm going to have a new string. This is going to be 2 4 6 1. Thereafter I'm going to increase all items one by one, and I'm going to have a new string 3 5 7 2. In that way I'm going to increase all items one by one, and finally I'm going to have the similar string if I increase items in the last string. So if I increase the items in the last set, I'm going to have the identical set given in the first column. So I can produce 7 different sets from a given set. Similarly, I am going to choose another set in the second row, and it consists of different combination of 7 choose 4. Thereafter I'm going to produce 7 different sets from this events. In that way I'm going to expand my examples, but always I can produce 7 different sets from a given set. In that way I'm going to have many lines but always have 7 columns. In other words, this line can be divisible by 7 and second line is divisible by 7 and the last line is going to be divisible by 7. If I find 7 choose 3, thereafter I'm going to have 7 columns as well. That's why 7 choose something is divisible by 7 itself. And remember that 7 was the p-value in my expression. That's why all these combination coefficients can be divisible by p itself. In that way, we proven the Fermat's little theorem because this expression is divisible by p. We just proven it according to the assumption. So we have proven Fermat's little theorem by induction in this video, and we also use necklace method and Pascal's triangle to show coefficients can be divisible by p. Thank you all for watching and see you next time.